Hello, so in this video I'm going to be discussing a metal that could be used in all future computers. There are some hints and suggestions here on this slide. So that metal that I am discussing is molybdenum. That's the metal. Here you can see there's an image of it. That's it in like a different form. In this video, I will be discussing molybdenum and how it could be used in chip design. And I will also discuss the impact this could have on all future computers, potentially. So, this metal, you see, um, as discussed before, molybdenum could be used in all future computers. So this element is starting to be used more in the chip industry to design nodes. You see, molybdenum is starting to be used more to design nodes. And those nodes are then used to make a chip, and then the chip is used for the computers and all sorts of different things. Computers is just one example of something that it could be used for. You see, molybdenum wasn't commonly used for this purpose. Normally, ruthenium was used. You see, that's pretty expensive, and there's a significant amount of waste that's produced when using ruthenium to design nodes. And you see, ruthenium, it's expensive on its own, and when it produces a lot of waste, it becomes even more expensive. So that's a problem. It's essential to find a different material or a different element to be used to design nodes. You see, there have been tests and studies performed on quite a few metals that I will discuss in this video, and I will share the results of those metals, and then I will go into molybdenum, that element, and why that one seems to be the better one that's preferred. So here are some clues for the next topic that I will discuss. So this says copper right here, find copper, that could be a suggestion. There's tungsten. This, by the way, is cobalt. That's an image of cobalt, another element. So now I will discuss the results from the test. So mainly three elements were tested. There were copper, tungsten, and cobalt. See, copper wasn't the best to design nodes. That's because it has something called a short runway. Short runway. It's basically what this is it's reached its limit for manufacturing chips. It can't really go above in terms of performance, essentially. It's basically at its limit already. And then tungsten and cobalt are kind of similar in some ways. They're better than copper, but they also have some challenges. For example, electromigration is a challenge in tungsten. When using tungsten as an element to design nodes, electromigration is a key challenge. And as you see here, it says what electromigration is, briefly describes it. It's basically when area gets lower, density increases. That's a problem. We don't want that in chip design. So that's one challenge with using tungsten. And both tungsten and cobalt also, to some extent, have short runways similar to that of copper, though not as significant as copper. But you see, the perfect element to be used is molybdenum because it's seems to be just right for designing nodes. You see, molybdenum, this element has resistivity. Its resistivity is better than that of tungsten. It is less expensive than ruthenium, and it is better when it comes to dealing with the electrics, which is important when designing nodes. You see, ruthenium doesn't even have this feature. Ruthenium isn't as good with the electrics as is molybdenum. You see, so molybdenum might even be perhaps a better element to use. See, so now I will discuss some deeper considerations and go a little bit more in depth. So yes, as discussed before, electromigration is a big deal. What this means is that molybdenum must be able to deal with solid precursors. So there are different precursors. There are these solid, gas, liquid precursors, and the ones that are used in designing chips currently most often are the solid precursors. And it is essential that molybdenum can be able to deal with them, and interact well with them, essentially. So the way this can be predicted would be to perform tests. And you see, there could be tests performed that can predict the behavior of a metal. And it can predict how the metal will behave with other metals and other precursors and stuff like that. This does eventually become a challenge, though, when it depends on the design you're using. If it's a backside power design, then doing these predictions becomes more challenging. So that's still in the process. Essentially, these tests are still being performed, and there's still some ambiguity about whether molybdenum can or cannot, and whether it should or should not be used, to design nodes for chips. But there have been quite a few already, quite a few tests performed already, and so far seems to be a pretty good element to use in chip design, the semiconductor industry, and in general to design nodes. Seems to be pretty good. Here's some statistics to support that claim. So, using this metal is predicted to lower memory hole pitch by about 3.7%. This essentially leads to 16.3% greater density, greater bit density. So the memory hole pitch is lowered by roughly 3.7%, if not more. A lot of times it's more than 3.7%. And there's a 16.3% greater bit density. These are all positive results so far. So molybdenum might be the perfect element to use, perhaps. That is it for this video. I hope you enjoyed. If you did, make sure to leave a like and subscribe, and see you in the next video.